Dear all, good morning and good afternoon, and thank you for joining our webinar dedicated to a new version of START-PROF, comprehensive software for pipe and stress analysis. Today we are happy to announce release of START-PROF version 4.85, and this is our second large program update since June 2020. The reason of such frequent releases is that our START-PROF team works intensively to meet requirements that come to us from pipe stress engineers from all over the world. During the webinar, we will highlight the most important enhancements, in particular, implementation of dynamic analysis capability to START-PROF. And I would like to invite Dr. Alex Matveyev, START-PROF product owner, to start the presentation. Alex, welcome.
Thank you. My name is Alex Matveyev, and I am the product manager of START-PROF pipe stress analysis software. I work on the development of this software training and offer technical support since 2005. Here is my email. If you have any questions, you can write me an email. In advance, let me say some words about START-PROF software. It is developed since 1965. At this moment, we have more than 3,000 users, and the number is growing very quickly. The licenses of the software in use is more than 10,000. The user interface is on English, Chinese, and Russian languages. START-PROF can perform pipe stress analysis according to 32 piping codes, and it can consider the winds, seismic, snow, and ice loads according to 18 codes. The software is widely used in process industry, in oil and gas, for oil and gas pipelines, for district heating networks, natural gas networks, water pipelines, and power generation piping systems. This is the agenda of upcoming webinar. This is the new features in the new version 4.85 of START-PROF. First of all, we'll talk about the modal analysis, dynamic analysis. The next feature is ASME B31.1-2020 new power piping code and how we implement it in START-PROF and the major changes in this code. Also, we'll talk about the remaining strength of corroded pipeline analysis according to ASME B31G. Also, we added the new ball joint element and Snubber element. And also we improve the built-in calculator functions. This is not all the changes. The full change list can be found in our knowledge base that you can find at our website, pestsuite.com. Also, we added the several manufacturers of spring hangers. Now START-PROF can select that springs, and we plan to add more spring hangers in the future versions. We added all the European codes to our database. Now you can select pipes, tees, bands, and reducers according to European code. In the previous version, we already had the ASME codes and Russian codes, and now we have all European codes. Also, I will talk about START-PROF API interface, programming interface that allow you to integrate START-PROF in your workflow. If you have programmers, you can integrate START-PROF. Also, I will talk about new features for import models from Excel and Autocad. We improved the START-AVIV interface with PDMS, Everything 3D, and Marine. And we significantly improved the import from CAESAR II software, and now START-PROF support the versions 8, 9, 10, 11, and 12. So let's talk about the dynamic analysis, the modal analysis. Let's let's look at this picture. You can see the one mass system, the mass and the support stiffness. You can see here, and we can add 4 forces that acting on this mass. The first force is the external load that is applied to our mass. The second load is inertial force. It equal to mass multiplied by the acceleration. The next force is damping force. It's the damping multiplied by the velocity. And the last force is the K by X. K is stiffness of the support under this mass, and the X is the displacement of this mass. So we can write the balance equation. All the forces acting on this mass must be balanced. So the equation will look like this. And after that, we can assume that we don't have any damping in this system, and we don't have any external loads. We can simplify this equation. It will be mx equal to kx. And after that, we assume that x is the sinus function of omega t. Omega is the frequency, t is time, and a is the amplitude of vibration. We substitute this function in our equation and got the equation like this. So now we have simplified equation. We can transform it to another form, and the first solution is the x equal to 0, but it is not interesting for us because it means that we don't have any motion of our system. So the solution of natural frequencies will be k minus m omega multiplied, equal to 0. Equal to 0. So the omega will be k divided by m and square root. So this is the equation for first natural frequency of the system. It has only one natural frequency. Also, we can calculate the technical, or also called ordinary frequency. If we will divide it by 2p, it will be technical frequency that is measured in 1 divided by seconds. And also we can calculate the period of vibration is 1 divided by technical frequency. If we have the system with 2 mass, we can create the same model, but the number of forces are greater. And now we can create the equation, but this is actually the system of equations, system of 2 equations. And M now is the matrix, the mass matrix. K is the stiffness matrix. C is damping matrix. And F is external force vector. And X is a displacement vector. We can perform the same simplifications to these equations, same transformations. And also we can assume that masses are equal and stiffnesses are equal. It will allow us to simplify this problem. So the solution can be obtained from this equation. It means that determinant of this matrix should be 0. I will bypass the complex computations, just show you the result of this solution, the solution of this problem. And you can see the value of the first and second natural frequencies. And also we can calculate the mode shape vectors. The first mode shape vector equal to A amplitude multiplied by that values. But the amplitude is unknown. We don't know the value of the displacements. We just can create the shape of the deformation, but we can't measure the value, for example, in millimeters or in inches, the value of the displacements in the system. We can only see the shape of the formation. And another property of mode shapes is orthogonality. If we multiply two vectors by each other, and the result will be 0. So all mode shapes are orthogonal to each other. How to define the model analysis in START-PROF software? To do this, you need to open the operation mode editor and select this checkbox, dynamic analysis. At that operation mode for which you want to see the mode shapes and natural frequencies. Also, you can define some properties. You can specify in project settings in the dynamic tab how many frequencies do you need, and also the special friction factor. I will tell about it a little bit later, and cut-off frequency. So now let me show you the example, the simple example. I will create a new piping model. And I will use the ASME B31 free code. Now I will add the first pipe object. The length will be 10 meters. For example, diameter like this. I will not use database right now. The pressure and temperature I will leave 0 values. It is not interesting for us right now. And I will remove the weight of the piping system. It will be weightless. Now I created the first pipe. I add the anchor on the one end, and I will add the node in the middle of this model. Now I will open properties of this node and specify 50 kilogram mass in this node and 50 kilogram mass in this node. So I have created the model the same as in previous example. Now I open operation mode editor and select this checkbox, dynamic analysis. Also, I can open the project settings, open the dynamic tab, and specify how many frequencies I need to calculate, and specify cut-off frequency. At this moment, that properties, I will not set that properties because it will not be used for that simple model. So now I'm ready to run analysis. Okay, analysis is done. I open the mode shape animation, open the dynamic, select the dynamic, and run animation. You can see the first mode shape. Now we can select the second mode shape. As you can see, it is perpendicular to the previous mode shape. This is the orthogonality property of the mode shapes. We have pair of natural frequencies that equal to each other, but the mode shapes are in different planes. And the second shape and the third shape, the same as you have seen on the pictures that I showed before. This is two mass system. And also you can open the output and select natural frequencies. You can see the angular frequency, technical frequency, and period. Now I will remove the weight concentrated masses, and I will add the uniform weight of the pipe, first pipe and second pipe, and turn on the function to display the masses on this system and run analysis. Now you can see that START-PROF automatically adds several masses. You can't select this mass, you can't modify it because it was automatically created in the second layer model. User of the software can see only the first layer of the model, but when you run analysis, START-PROF automatically create the second layer model more detailed, it automatically modify model. In this case, START-PROF automatically adds additional nodes and add masses. You can see them, but you can't change them. You just can see the value of the masses. So now I can run analysis, and you can see the mode shape. This is the first mode shape, the second in perpendicular plane, next pair, the third pair, and so on. So we can see several mode shapes. And the more masses we add to this piping system, the more accurate natural frequencies we will receive after analysis. Okay, now I close this model. So how to distribute the masses over the piping system? You don't need to do this manually. START-PROF will do this job automatically for you. You just need to specify the cutoff frequency in the dynamic tab of project settings menu. START-PROF use the simple method. For example, we have the beam on two supports like this, and it have the distributed mass over it. M is distributed mass. So we can get the equation for the first natural frequency of this beam. It is well known in literature. So this is the equation for the first natural frequency. This is the stiffness of the beam. This is the distributed mass. L is the length of this beam. This is the length. So now we can transform this equation in another form and add the 0.5 factor here. Now, if we will specify the cutoff frequency, it will go here into this equation. And after calculation, you will get the maximum span between masses. So you need to split your piping system into several parts, and each part should not be greater than this value. START-PROF do this automatically, so you can specify the cutoff frequency. For example, here I specify 33 Hertz. This means that all frequencies under the 33 Hertz will be calculated almost accurate, but frequencies greater than 33 Hertz will be not so accurate. If you need, for example, frequencies up to 100 Hertz, you need to specify the cutoff frequency 100 Hertz. So START-PROF take the distributed mass of the pipe and concentrate it into that nodes. So START-PROF use the concentrated mass model. As distributed mass, START-PROF take the pipe weight, insulation weight, fluid weight, and additional uniform weight, calculate the sum of that values, and distribute as concentrated masses in your piping system. So here you can see the mode shapes, first, second, third, and mode shape for with higher frequency for the distributed mass beam. So in START-PROF, if you will create such model, you will see the same result. As in previous example, I already show you the cantilever beam model, and you may see the mode shape, something like this in the previous example. Now, how START-PROF deal with bands and tees? In the band element, START-PROF can add 2 masses, or it can add 3 masses. START-PROF decide automatically what to do, depending on the length of the band and the calculated maximum distance between masses. The same decision START-PROF make for tees. It can model the tee with 1 mass concentrated in the intersection point between pipes, or it can put 4 masses. The valve can be modeled by one mass or two masses. The decision making automatically by START-PROF. So, for example, if you set the cutoff frequency 10 Hertz, the number of masses will not be so big. The calculation will be performed quickly, but the frequencies will be not so accurate, especially the frequencies that are greater than value 10 Hertz. If you specify 33 Hertz, the number of masses will be greater. The analysis time will be greater too, but the accuracy will be greater. And you can specify the cutoff frequency, for example, 300 Hertz. The number of masses will be much greater, and the accuracy of results will be much better. Distribute the masses in piping system. In this model, the cutoff frequency is 10 Hertz. So you can see that START-PROF add one mass in the T element. This is the T element. It has the length and branch length and T height and header length. But it is modeled using only one mass. And here is the valve. It also modeled by one mass. And this is the long radius band. Long radius band. The radius is about 50 meters, and the band length is 15 meters. Now let me specify the different value of cutoff frequency, for example 100 Hertz, and run analysis. Now you can see that T is modeled using 3 masses, and valve modeled using 2 masses instead of 1 mass. And we have much more masses along all the pipes in this system and along the long radius band. So now let's talk about nonlinear system analysis. Modal analysis can be applied only for linear systems. What I mean linear, it means that it doesn't have any nonlinear behavior of the piping system. But a real piping system has a lot of nonlinearities, like the supports that can lift off the friction and other nonlinear effect. Let's see how START-PROF deals with that. For example, if START-PROF lift off in operational mode, we think that this support is not working, and when START-PROF performed dynamic analysis, it removed this support. It performed dynamic analysis without this support. The next option is that this support is working in operational mode. For example, the weight of this pipe is great, and pipe fallen down, lying down on this support, and it's working in operational mode. In this case, START-PROF will consider this support, but it will replace the single directional support by double acting restraint and perform dynamic analysis. Of course, if the displacement is not so high of this support, and if the amplitude of vibration is greater than this displacement, this pipe will bite by the support, beat the support, but we ignore such effect. We think that this support exist or not exist. We can't model the nonlinear effects in modal analysis. Another problem is the friction. Actually, friction forces affect the natural frequencies results very significant. The results may be changed several times. How we deal with that? START-PROF can replace the friction force by the springs with predefined stiffness, the K. The stiffness calculated using the following equation. we calculate the support force, the load is acting on this support, multiplied by the friction factor and multiplied by the special friction coefficient. This coefficient you define in project settings. So the analysis results will depend on this factor. How to understand what's this? Which value to take? This is the vibration amplitude A. This is displacement and this is the force. So we think that during pipeline vibration, the maximum displacement should not be greater than, for example, 0.025 millimeters. In this case, we can divide 1 by the value, by this value, and get the value of this factor. It will be 40. 40 is the recommended value, but nobody can say which value is accurate. To define this value accurately, you have only one option. You need to perform measurements, field measurements on real piping system that is vibrating. You need to measure the natural frequencies of the real piping system, and after that create the model and tune this factor to get the approximately same natural frequencies in the START-PROF model, almost the same natural frequencies as in real system. You need to try define the different factors and find the value that gives you a most accurate results. And only after this you can consider that your model is perfect, and after that you can use this model to tune your system and change natural frequencies and see how does it affect the results. Usually this job performed to reduce piping vibration. For example, you had a system that has vibration and you need to decide what to do, how to modify the system to reduce vibration. So firstly you need to tune this factor to get the accurate natural frequencies, and only after that make different changes in the piping model and decide what to do. Okay, so now let's proceed. Also, START-PROF consider this factor to friction to the expansion joints that have the friction inside. It's a slip joint, ball joint, and torsion joint. START-PROF automatically apply this factor for expansion joints too. And another nonlinear effect is the rotation rod that replaced by 2 springs with K stiffness, but calculated as the vertical load on this rotation rod divided by the length of this rod. For example, the spring hanger in START-PROF has the rod length property. So if you input here the value, START-PROF will calculate the stiffnesses of the springs according to this equation. So now we calculate the natural frequencies, what to do next. Some companies have internal requirements that natural frequencies should not be lower than 4 or maybe 5 Hertz. And also this recommendation is added to the DNV-GL recommended practices that the natural frequency, lowest natural frequency should not be lower than 4 or 5 Hertz. If a natural frequency is lower, then the risk of possible problems with vibration due to rotation equipment, to slug flow, wind loads, and other dynamic effects, the risk will be high. So it's recommended to keep the first natural frequency greater than 4 to 5 Hertz. How to increase the natural frequency? Let's check how to do this. I will tell about this a little bit later. And now let's check how to deal with rotation equipment. For example, we have pump or compressor with vibration frequency, with known vibration frequency. So the ratio of equipment vibration to the natural frequency of piping system should be not with that range from 0.8 to 1.2. Why? Because if the natural frequency of the piping system is equal to equipment vibration frequency, we will have the resonance effect, and the amplitude of vibration will be infinite. And if we within that range, the vibration amplitudes will still be very high. So we need somehow to change natural frequencies of our piping system to get out of that range. Some codes also have another requirements. For example, the Ghost code has the requirement that for higher frequencies, the range is a little bit smaller because it's not so easy to satisfy that requirement. So the Ghost code allows you to use less conservative equation for higher frequencies, where you can find that requirement. The first document is Energy Institute Guidelines for Avoidance of Vibration-Induced Fatigue Failure in Process Pipework. And the second document is API 618 code. You can find there this requirement. Now, what should we do? How to change the natural frequency of our piping system? For example, we need to increase the frequency. If we will look at this equation, you can see that we can increase the stiffness of the supports. For example, like this, if we will increase the stiffness by 4 times, we will increase the natural frequency by 2 times. And also you can reduce the mass of the system by 4 times. It will also increase the natural frequency by 2 times. If you have another goal is to reduce natural frequency, you need to reduce the stiffness or increase the mass. Of course, in practice, only increasing the stiffness of supports is used. The other methods is not so popular. So this method is the most popular. You need to add more supports and increase the stiffness of the supports to increase the natural frequency. Reducing of natural frequencies are very rarely used because it is not so easy to reduce the natural frequency, but it's much more easier to increase the natural frequency. For example, we have the piping like this. It has 1.2 Hertz. Usually the piping system was designed to withstand only dead weight and thermal expansion, will not have any restraints in horizontal direction. This leads to the problems with natural frequencies. If we will add additional supports like guides, limit stops, we will increase the natural frequency, and our system will satisfy the requirement that natural frequency should be higher than 4 or 5 Hertz. This is guide support, guide plus limit stop, and this is guide support. So now let me show you live example. Okay, I will hide the masses. So now analysis of this system is already done, so I will just show the results. This is the thermal expansion. And also please note that this support and this support, you can see here, the two supports are lifted above the pipe lifted above the support. So these two supports are switched off. Now let's check the mode shape of this piping system. I choose dynamic, run animation. You can see this is the first mode shape, and the frequency is 1.2 Hertz. It is not high enough. How to change it? We need to find the point where the displacements of the mode shape are the greatest. We have a mode shape like this. So the greatest displacements are in this point. So we need to add the guide in this point. Okay. Now I delete this support, add the guide support here, and let's run analysis and check the results. We can check the natural frequencies. It is 3 Hz already. It is higher, but not high enough. Let's check the mode shape. Now it looks like this. What to do now? We can see that the greatest displacements at this point and this point. So we need to add the guide here and somewhere here, for example, at this point. Okay, so now we return to editor and add additional guide supports. I delete this support, add single directional guide here, and add single directional guide here. Okay, now let's run analysis. It seems like we should get the perfect model, but it's not so easy. We have only 4 Hz, and for example, we need 5 Hz. So now the first mode shape looks like this. So we need to add additional support. Let's delete this support and add limit stop and guide support. I will add double actin by X, double actin by Y, and single directional at -Z. Okay, like this. Now we run analysis and check the mode shape of this system. Now you can see that first natural frequency is 12 Hz. Now it is satisfy the requirement. This is the first natural frequency, second, third, and so on. But we did this considering that the friction coefficient is 0, as required by several companies. So each company has internal rules, and it requires that the friction coefficient should be 0. So now I will remove all supports, and let's specify the friction coefficient 40 as recommended. It's actually the value 40. 41 divided by millimeters is 1001 divided by inch. So I specify 40. It is approximate recommended value. So now let's run analysis. And we can check natural frequencies. And this is surprise. We have natural frequency 24 Hz. So if we have the friction, we don't need to add any supports to this model, because friction hold all supports and doesn't let it to move in any direction. Now I run analysis and we can see how does it work. This is first mode shape. The second, as you remember, I said that 2 supports was switched off. So now we can see only vibration, all of the supports that was switched off. So this example show that how important to consider the friction properly in your piping system. But nobody can tell you which value of this factor you should take. You need to compare your model with real piping system that is under vibration, calculate the first natural frequency of that system and compare with your model and get this the value of this factor. Okay, so now I will close it and let's proceed. Another point is that if we have connection to the equipment like pump or compressor, we need to consider the flexibility of this equipment. For example, sometimes the frame of the pump or compressor is placed on the special rubber anti-vibrating supports. We can find the stiffness of that support in in horizontal direction and in vertical direction. We can check the stiffnesses of this support, and we can define it in our piping model like this. We can model the frame of the pump and specify the stiffness of each support. Let me show you this model. This is the model, and let's check how does it work. It's already calculated. I will not perform the analysis again. Now we can see the operation state, and this is the first mode shape. As you can see, it is lower than 4 Hertz. This is the first mode shape, and you can see the big deformations of the pump frame. This is the first mode, and so on. So the first mode shape was 3.71 Hertz, 3.71. Frequently, the pumps modeled as an anchor without taking into account the real flexibility of the pump. Let me delete this model, and I will leave just the pump. And in this case, START-PROF will model the pump like an anchor, like we do this in ordinary static analysis. This is the, let me check, this is API 650 pump. And now I run analysis. As you remember, our natural frequency was 3.71 in the previous model. It was lower than minimum accepted natural frequency. Now, if we have ordinary model, you can check natural frequencies, and you can see that everything is okay. We have natural frequency 10 Hertz, but this is incorrect result because the real natural frequency is much lower because we didn't take into account the stiffness of the pump frame. Here is the first, second, third, and other mode shapes of this piping system. So it is very important to take into account the flexibility of the pumps, pressure vessels, and other equipment to which our piping is connected, including the steel structures. The dynamic model of START-PROF was verified with published examples in literature, and results are the same as in published verification examples. So let me check the next feature of START-PROF is the new ASME B31.1 code for power piping systems. I will remind you about the issue of the previous edition that is described in my article that you can find in our blog at psu.com website. For example, you can create this piping system, the pipe restrained between two anchors. If you will run analysis in any pipe stress analysis software, you will receive the 0 expansion stress. So this system satisfies the code requirements. But it's obvious that it doesn't satisfy because the axial force will be great until it will be greater than allowable. In previous version of START-PROF, you could add the axial force. We did the special feature to add the axial force, and you can see that expansion stress is much greater than allowable. So this equation doesn't take into account the axial force. And the same problem is with sustained loads. If you have the great weight that is acting on your pipe, the stresses can be much greater than allowable, but you will not see it in pipe stress analysis software because the equation of the code doesn't take into account the axial force. In new edition of ASME B31.1 code, this problem was solved the equations are completely different for sustained loads, for occasional loads, and for expansion stress. It takes into account the axial force. It takes into account the torsion moment. So now there is no such problem like I described for the previous version of this code. And equation is like in ASME B31 free code. Another significant change in new version of this code is that now stress intensification factors and K factors should be calculated according to ASME B31G code. The stress intensification factors that was used in previous version of this code are no more applicable. So now you need to analyze using ASME B31G. Fortunately, START-PROF allow you to do this very easy because START-PROF model each T of in your piping system using the complex model. It replaces the model of your T by the model like this. It adds the rigid element here to replace the void inside the header. It adds the flexibilities of the header. It adds the flexibility of the branch. According to the ASME B31G, it calculates the K factors and apply it here. And this is done automatically. You don't need to do this manually. You just run analysis, draw your piping system, and run analysis. You don't need to do anything to improve the results. So and also START-PROF add the additional nodes here, here, and here, and consider the greater wall thickness of the pipes equal to wall thickness of the T. It is not very important for ASME code, but it's important for European codes and Russian codes. There, the T's can have the wall thickness much greater than the connected pipes. And we need to take into account the stiffness of this part of the T. In rigid systems, it can affect the results and support loads significantly. The next feature of START-PROF to added a new version is evaluation of the remaining strength of corroded pipeline according to ASME B31G code. So, for example, you have some defect on your pipeline. You can measure this defect, and measure the pit depth, calculate the distances between measuring points, and input this data in START-PROF software, define the diameter, wall thickness, the design pressure, the minimum yield strength at ambient temperature, the material ultimate tensile strength, design factor, and run analysis. After that, you will receive the burst pressure, the safe pressure, the maximum allowable pressure for your piping system, and failure stress. And also, START-PROF will calculate the maximum defect length. The analysis is done according to several methods. The first two methods is original B31G and modified B31G and the effective area, and also some additional methods. For example, we have the pipe without defect. In this case, the allowable pressure can be calculated as allowable stress multiplied by two wall thicknesses and divided by outside diameter. It's Berlow's formula. If we have a defect and we know the defect length and maximum depth, we can calculate the allowable pressure according to this equation, where A0 is the area of the wall thickness that holds the pressure, and the A is the area of the defect that is removed from our pipe. And now we can substitute that values in this equation and also consider the M factor. The M factor was obtained from tests, from real-life tests. and the allowable stress calculated as 1.1 multiplied by specified minimum yield strength. For long defects, the shape of defect considered as rectangular. The modified B31G method has different equation. Now the area calculated using this equation and the allowable stress calculated using this equation, and we use different value for M factor. It depends on the defect length. And for very long defects, we use different equation. And the most accurate effective area method, in this case, we need to measure our defect, measure the distances between measuring points, and measure the pit depths along this defect, and input this data in software. It will calculate the area of the damage and consider several cases. So we need to check all the possible combinations of the areas. For example, we input the following values in software, and START-PROF will check, for example, the first case is this. Let me show. This area is the defect area. START-PROF will substitute it here, and this area is the full area without defect. So now START-PROF calculate the first case, calculate allowable pressure. After that, it check another sector, then another sector, and check all the sectors along this defect and calculate the pressures. After that, it calculate the 2 sectors combined, then 3 sectors, 4 sectors. So we need to check all possible combinations of defects, including the final case when we have the full defect area. But the calculation shows that this last case is not always the worst case. Sometimes some of the intermediate cases became the worst case. And we take the lowest pressure value from all the cases. This is done automatically by software, and you receive the results. I will quickly show you how to do this. Just open File, New, Elements, then select ASME B31J code, and open this element. But I will not type data myself. I will just open a predefined file, and here you can see the 24-inch pipe. This is the wall thickness. This is the yield strength, tensile strength, design factor, and the measurement of pit depth values. And you receive results of burst pressure, safe pressure, failure stress according to different methods. So you can change the value, for example, define the design factor and run analysis. You'll receive different values. You can change the values of the defect depths and run analysis, receive another results. Okay. So now let me close it and continue the presentation. The next feature that we add a new version is ball joint. The ball joint allows two pipes to rotate around each other. So 2 pipes can rotate, but unlike the ordinary expansion joint like bellows that has the stiffness in this point, the ball joint have the friction moment. So if we will apply the moment on this pipe that is less than friction moment in this ball joint, it will not rotate. If we apply the moment greater than friction moment, where rotation will begin, and ball joint will rotate, and it will transfer. For example, we have nozzle here and some equipment. It will transfer the moment to the nozzle and this moment will be not greater than the internal friction moment of expansion joint. Now, let's see another feature. The problem is that the friction moment depends on the pressure. So if we have a piping system that operates under different pressures, for example, we have operation pressure, design pressure, and other pressures, we need to specify different friction moments. START-PROF solves this problem, and we allow you to specify the friction moment and corresponding pressure. You can define up to 3 friction moments and 3 pressure values. START-PROF will automatically interpolate the friction moment between the pressures. So you don't need to care about calculating the friction moment by yourself. You just select this ball joint from database. All that values will be taken from database, and then you can just run analysis. START-PROF will automatically calculate the friction moment depending on the pressure value. And START-PROF, after analysis, START-PROF will check the rotation of this ball joint. It should not be greater than allowable rotation, but it is also taken from the database. And the torsional rotation is not limited for this type of expansion joints. For example, the torsion moment, the torsion angle is unlimited. So now we have all type of friction expansion joints. It's slip joint, torsion joint, and now we have the ball joint. And also the same as for slip joint and for torsion joint, the same, we add the database for the ball joints. We added the high-span barcode ball joints and Chinese ball joints. So you can just take the needed ball joints, insert the ball joint object in START-PROF, and click to get it from the database. That's very quickly, very easy. You don't need to deal the friction moment values. Another feature that we add in new version is the Snubber object. Now you can define the Snubber. What is the Snubber? It's used for reducing of displacement stresses and support loads from earthquake events. If you apply the load or displacement on this Snubber very slowly, it will deform without any resistance. But if you will apply the load quickly, it will work like a rigid element because it has a liquid inside the Snubber, and liquid doesn't allow you to quickly deform this Snubber. How to define it in START-PROF? You just insert the special object Snubber and run analysis. Let me show you. This is the simple model. For example, I will add the Snubber element. Oh, sorry. Insert Snubber. I select rigid Snubber in Y direction. And now I will add the additional operational mode. For example, this one. Select it will be occasional mode, and I will select that Snubber's active in this mode. And now I will apply some force in Y direction for this case 1.1. It will be, for example, 5 ton. And now let's run analysis and see how does it work. This is the operational state. This is the installation state. This is operational state. You can see that Snubber doesn't it just it moving with the pipe, and there is no any resistance to the pipe movements because the thermal expansion load applied very slowly. So now we have the operational state. This is installation state, installation position, and this is operation position. And now let's check our occasional load case. Now let's run animation. We applied the force at this node. We applied the force. It is occasional force. So now our snubber hold the pipe in operation state. So the displacement is operational displacement, but it doesn't let this node to move under this quickly applied load. And also we can open the animation of the mode to see the mode shapes of the system. Now you can see that snubber hold the pipe during the dynamic analysis. Okay, so this is snubber element. The next feature that we have, it's built-in calculator in the fields of START-PROF software. In previous version, you was able to enter some equation like 1 plus 2 multiplied by 3, calculated and receive the value 7. In new version, we expand abilities of this calculator. Now you can specify the values in any units. For example, the units for that field is inches, but you can define value in millimeters. You just type 5 millimeters. It will be converted in units automatically. And you can specify the feet and inches like this, and it will be converted automatically too. And also we add some the new representation in feet and inches. Let me show you quickly in START-PROF. How does it work? Now let's open the pipe properties, and now you can specify here, for example, 2 feet. Now I click enter. I push the enter button, and it automatically converted to meters. And also you can specify here 1 feet plus 2 meters, and you will receive the result. And also another feature, let me show the pipe span length. It is 2 meters. But now I open the customized units and select the feet and inch representation. And now you can see that each pipe is 6 feet and about 7 inches. And also I can say that all the units can be converted on the fly in real time. For example, I see the stress table in kilogram per square millimeter, but I want to see it in different units. You can just open and change the units for stress and pressure. For example, the pounds by square inches. Click OK, and now it is converted in real time into another inches, even after the analysis already done. So you can do this at any moment. You can do this several times, for example, several times per minute. It's very easy and quick. Now let's proceed. Also, we added the new spring selection tables. You can see the manufacturer names here, and we plan to add more spring hangers and spring supports into our database in the future versions. Also, we added the materials according to European codes. In new version, now you can take any band, T, or pipe from the database. We already had the ASME codes, we already had the Russian codes, and now in new version, we added the European codes. So now we have 3 types of codes in our material database for pipes, T's, bands, and reducers. And also we improve the converter from CAESAR II into START-PROF. Now it can read the models from version 8, 9, 10, 11, and 12. Let me show you how to do this. I just close the model. I have some neutral format files of CAESAR II. This is the Caesar II neutral file, CII. I just drag and drop it into START-PROF, or you can just double click it. And START-PROF automatically convert the model. And now the algorithm is much smarter. It's convert the supports and all the properties of Python system much better than in previous version. Let me show you another model, for example, like this. Oh. This is another model, and I can show you one more model, this one. Okay, so now you can see that you can convert the model from Caesar II to START-PROF, and also you can convert back, export into Caesar II. So you can convert the model back to Caesar II. Also, START-PROF has the special API programming interface. It was built in START-PROF for many years, but in new version, we added the description of this user for this programming interface. How to use it? You can write the program in C# language or in BASIC or any other language that will work with START-PROF API. For example, this simple program create two nodes and add the pipe between nodes. But you can add the code to run analysis of this model, modify this model, run analysis again, get the data from this model, convert it into any other format. So you can do anything with START-PROF. For example, you can integrate START-PROF with your 3D model software that is used in your company, and you can create the silent converter. For example, you draw your model in your 3D modeling software and click run analysis. It will automatically invoke the START-PROF, convert the model to START-PROF, perform analysis, and return results back to your 3D system. And you will not see the START-PROF user interface at all. It is just example. So what you can do. Also, you can do create some converter from START-PROF to any other software, or vice versa, from any software into START-PROF. One company, as I know, they created we had the requirement from client that we have the Python system with a lot of supports, and client asked them to check the reliability of this Python system. The idea is that you need to remove some support, one of the supports, and run analysis, and analysis results should satisfy the code requirements. All the nozzle loads, all the stresses in this Python system must satisfy code requirements. After that, you return the support and remove another support and run analysis again, and so on. You need to remove all the supports one by one, and all analysis results should satisfy requirements. If you need to do this job manually, it will take a huge amount of your time. But with this API option, you can write a simple program that will do this job for you very quickly. Okay. Now, another feature is import from Excel. You can create the Excel table like this, and after that, open START-PROF and open this model, convert it in START-PROF. Especially this is very interesting for the main pipelines, for very long pipelines, where you have the data about profile of your Python system, and you need to convert it somehow into START-PROF to perform analysis. So now with this feature, with import function from Excel, you can do this very easily. You need to do this manually. You just import from Excel. And another one feature is import from Autocad. You can draw the center line of your Python system in Autocad and invoke the data extraction feature, convert this data into the table, the Excel table, and then open it using the START-PROF. This is all features what I wanted to tell you about. Also, you can watch the videos on our YouTube channel. We have recordings of our webinars, and recording of this webinar will be uploaded to our YouTube channel. Please subscribe and watch the other videos. And also you can subscribe our social media. We always publish some interesting articles about pipe stress analysis. And also I publish about 50 articles on what is piping resource. You can read them. Thank you for your attention. Marina?
Thank you, Alex, for your impressive presentation. I think that our participants enjoyed it. If you have any other questions, you can send us an email. And of course, if you haven't tried our software yet, please visit our website where you can download a free 30 days full version of START-PROF and other software included in PAS Suite. So thank you again and have a good day.